I'm here. So thank you very much. So my name is Damien Foucard. I'm a PhD student at TU Berlin. I'm in the research group ODS upon distributed systems under Professor Manfred Hauswert. And so I work a little bit with people from DeepMetis. So I'm very lucky to try to get some collaboration working between research and industry. So obviously it's a very fruitful area. And I wanted to tell you a little bit how my activities relate to explainable AI. And more specifically, I want to speak about data summarization. So when you have a lot of data, how can you just pick exactly the small chunks which are interesting for us? And how explainable AI helps us to decide what matters in this whole mess of data. And so interestingly enough, so there are many use cases where you have a lot of data here. Just for example, if you have network trace, you have a lot of packets going through a router, and these packets could end up on a server. And if you have somebody attacking us, they're going to produce a lot of packets going to server. The server is going to be overloaded, so you won't be able to use server. This is called denial of service attack. Or this could happen in a distributed fashion, where many different clients spread over the internet attack a single server, DDoS. So already in this case, what matters is we need to find out which client on the internet is attacking us. What matters in the huge mass of terabytes of data coming through every day. So especially if you think about huge companies like Google. Interestingly enough, we have the same problem. Sorry, well, the same problem also when we have a lot of text or images, where there is a mass of, if you think about Instagram or Twitter, we have a lot of media at hand, and we need to find out what is relevant for the user. So you can see that in the data science in general, there is a pattern of a lot of data needing to find out what's relevant for us. And also to touch upon what Julia Hoxha spoke about at the beginning, which is medical analysis. There is a lot of work going on how to find some patterns in medical data. So for example, some gender, some region where people come from, looking into the wide range of factors and how they impact the symptoms or the diseases. And so in this is also a mass of data which needs to be organized and which needs to be presented to users. So the relevant population needs to be presented to users. So if somebody is interested in finding out whether female between 20 and 30 are more likely to get a specific disease, we need to bring some information. We need to bring data for this section of the population. And also another even more general use case for summarization is when we look into a lot of different actions from users over the internet. So they're going to, for example, do a Google search for a product, and then they're going to click on an ad on Facebook. So there will be a lot of different actions connected one after the other. And the goal here is to find out which action is going to lead to a conversion, so the people are going to buy the product or not. And in all these examples, which I just mentioned, what matters is we have a large amount of data, and the user is navigating this data. And the goal is that AI is going to help the navigation converge as quickly as possible to what is interesting for the user. So, but AI might help to find out what matters using some classic techniques. So just as k-means, for example, just to name a very simple one. But in the same time, we can learn from what the human is telling us. So for example, if the human has been looking to stick to the medical data example, if the human has been looking at the population with age 10 to 20 and then 20 to 30, we can guess that what is interesting for them is going to be the next range. So the range, for example, so 20 to 30, 30 to 40, etc. So we are able to mix the properties of the data in trying to find out what matters, and the behavior of the human. So this is where there is this interesting overlap. The goal being to find out what is really interesting in general. So to present a summarized view, which is the interesting data. And just to To make the matter more concrete, let's consider a single use case in the broad list which I spoke about, which is a lot of text. We have a lot of text, for example, on Reddit, which are produced by people. And the problem is there are many texts produced, and now there is a user wanting to look at some text based on their interests. So we could try to group the text in topics. So for example, some about Trump politics, about Biden politics, different topics, but then there will be a huge, large tree of topics. And the person might be only interested in one very small subpart of the topics, which could be, for example, they're interested in fashion and dress. So we don't need to produce all these different topics, this large tree, which AI would produce on their own. So we can see based on what they were looking at before. So for example, if they were looking at many texts in fashion, then we're going to only present the tree reduced to the node fashion dress or to the Trump politics. So we can restrict the large tree of topics to what corresponds to what they were looking at before, to what the user was looking at before. Okay, and in our research, because I was working with a lot of students who were helping me, this is why I'm saying our research, we looked into how the human can help determine what matters alongside with AI, and so the human can tell AI what matters, and AI can tell the human what matters. So there is really a symbiosis here. And we looked into the symbiosis along 4 main axes, which is what we call the reflective summarization, because what we do is we summarize the data. So summarize the data by looking at, for example, which texts were the most frequent. But then we use the summary. Based on the summary, we're going to look at all the texts which were, so we have the summary at hand, and then we get new text, and the new text, we're going to decide whether they matter or not based on the text that we have at hand. So our determination of importance is going to be based on the summary that we already have. So the summary drives the importance mapping, and the importance mapping drives summarization. So this is one important aspect which makes the whole problem difficult to address. And we also looked into this dynamicity optimized indexing. So what we mean with that is, if we have, for example, the Spotify use case where you'll have a lot of songs and you have a user listening to some songs, we have a model for what the user is looking into. Then we might want to update the model according to we might want to update the model according to what we might want to update the model if there is a song from some very well-known artist like Ariana Grande. Then we need to update the model for the customer right now, because if we don't do that, then the competitor is going to do this. For example, Apple Music is going to do this instead of Spotify. But if it's a song which is much less important from a very much less influential artist, then we don't need to update it right away. And so there is the problem of trying to optimize when and how we update the model based on the importance of this update. So if the update really matters to the user, then we want to integrate that right away. And we looked into those topics. And also when we speak about science, often we want to get some guarantees of performance. So is the importance that we measure within some bounds of some ground of importance? So just to keep the matter simple, we could be speaking about the frequency of words, for example. And we want to find out whether the frequency of the words that we measure on the stream is close to the ground truth frequency, which we would have if we had an unlimited storage. And this would be some importance tracking with bounds. Great. but this is very limited. So this is some very controlled environment, but it's also a limited environment. And this is to be opposed to the environment of some much more advanced machine learning algorithms, which would take into account text and would it would be feeding the text using some weighting mechanism, so some transformer mechanism if you want to look it up. This is the name of a neural network. And it would be automatically adjusting the weights of the different words in the learning process. This is much more a black box. In that case, we get some representation of the text, which is very powerful, just like it was the delta bond, which was touched upon in the previous talk, but which doesn't give so many guarantees. So we can't say that we are capturing the text within a specific that we're capturing the most frequent words within specific bounds on the accuracy of the words, for example. So this is the ML hybrid embedding computation. So ML hybrid meaning that we look into how to combine these very simple setups where we have some guarantees, such as counting the frequency of the words, and the very advanced setups where we have a lot of power, but very much less control, as in the transformer neural networks, which is one of the most modern neural networks for capturing text information. And finally, we are aware that the user can tell their interest in many different ways. So actually, when an expert issues some SQL queries one after the other, or so when experts issue some queries one after the other, it corresponds to some customer trying to looking at the text one after the other. In both cases, what is expressed is an evolving interest. So an interest which gets more refined. So for example, if we have a new user on a Reddit platform, they're going to first get one text, which they're going to look at quickly, then move on to another text, and so on and so forth. And at the beginning, the system doesn't really know what's interesting for the user, so the information is very coarse, and then the information gets refined. And in the same way, a medical expert, who would be looking at the population, they would be looking at a histogram, for example, of disease. 1 second. They would be looking at the histogram of diseases. Okay, I will just continue. And they would be interested in trying to find out first on a very broad population without so much information what is the distribution of the disease, and then trying to narrow down to the population of interest. And we try to take into account this input from the user which take different form into this single simple kernel, so to say, which captures the evolving interest. Okay, and so we implemented this. Obviously, I won't go into details for the interest of time, and the slides are going to be put online anyway. But we looked into how XAI can help for the summarization. Okay. For 3 main data structures, which are sets, which could be seen also as lists, trees, and graphs. And again, fully aware of the necessity for the interest of time. But what we did is we looked into sets first. We'll go very quickly. We looked into not simply taking into account a single item, trying to count them, but which gives us the guarantees as I was speaking about, but also into feeding the single items to your neural network and trying to capture the counts for that neural network. And so this is still, so the ML approach in itself doesn't give any guarantees, but it's very, very powerful. And the classical approach gives some guarantees, but it's very limited in its flexibility, because we can only capture counts basically. And so what's necessary, as I was saying, is we need to combine them, and we try to marry the two in 2 ways. First, we have the ML only make decisions on the parameterization of the classics mechanisms. So we limit the impact of ML. And second major aspect, which really is at the core of XAI, is we learned what queries are going to be issued by the user. And based on these queries, we decide what to summarize. So if an item is very frequent, but is not queried, or we know based on our model of the queries that it's not going to be queried at all, then we won't bother keeping it, even though the high frequency gives it some importance. So we developed some importance mechanism, which is aware of both the intrinsic importance of the data, so for example, the counts of the items, and the likelihood that they're going to be queried. And so this is what I summarize here with this diagram. And generally, as I was saying, this is the second point. We were trying to find some sweet spot between between the ML and the classic, where ML is going to have small impact, and then classic mechanisms would back it up. And this is our results on trying to capture the query patterns. And to put it simply, in the interest of time, when the color remains more or less the same on the x-axis, that means that there is some similarity and that we are able to capture efficiently. And so our results here indicate that if we try to adapt based on our model of the queries, if we try to adapt more or less, we get to some optimum, which is a sweet spot point here at, for example, 0.80. Okay, and now also there are many more results and many more pointers for you. But in the interest of time, we'll just move on to the general conclusion, which was that, which is that we're definitely looking into, we already have some public data set, which is from Reddit. We have like 130 gigs, so it's significant enough. And we're definitely interested in any collaboration. If you have any pipeline where you're wondering how to capture what matters, which data matters, and how the human can tell the machine what matters and what doesn't. And so if you're interested in those topics, you can just get in touch. And that's it. I'm done. Thank you very much.